There is another way, of course. This is the indifference curve approach. You can always convert this problem into one variable optimization problem and then do it. Okay, that is also another way in which you can actually solve the same problem. Okay, and of course you'll get the same answer. Provided you do it correctly. Obviously, no matter what method you use, you should get the correct answer. Provided you you use the method correctly. Okay, so this is what you can do over here. You can first argue that your optimal choice will always lie on the indifference curve corresponding to mu level of satisfaction, so that you can write the expenditure minimization problem in this way. Okay, and now what you can do is, of course, x is non-negative, y is non-negative. Okay, now what you can do is you can just write y as mu minus 2 root x and then substitute it over here. Okay, so you will get the problem as follows: minimize with respect to x, okay, where x can take value between 0 and mu square by 4, pxx plus py, and what is y? It is mu minus 2 root x, mu minus 2 root x. Okay, so this is how you can write the expenditure minimization problem. It's just a function of one variable, and now you can easily plot this function, which is a function of one variable, and figure out where the peak is in this interval, where the peak is in this interval. Okay, that is all that you need to do. Okay, it's just a one variable optimization problem, and you can easily solve it. Okay, let's just try this out. Okay, let's take the derivative of this, because once you want to take the derivative of this, we'll get to know exactly how the graph looks and how where the solution should be. So it turns out that if you take the derivative, you're going to get px minus py by root x, right? Now notice that when x is close to 0, the derivative is negative, right? Yes or no? When the x is close to 0, the derivative is negative. Do you agree? So this is the expenditure. Okay, so let's plot the expenditure function basically. So when x is 0, then this is the expenditure, right? Py into mu. Right? Okay. And when x is close to 0, the derivative is negative. So what does this tells you? That if the derivative is negative when x is close to 0, this means that your expenditure falls as you increase x. Yes or no? Because the derivative is negative when x is close to 0, that means your expenditure is falling as you're increasing x. Do you agree? Yes. Okay, basically what we are doing is, if you just see this graph, we are moving along this curve and we are checking what is happening to the expenditure. And what happens here is this, we have already argued why this will not be the optimal choice, and this is another way to argue the same thing, that when x is close to 0, this term will be dominant, and therefore the derivative will be negative, which means that the expenditure will be falling as x increases. So that means you will never choose 0 units of x. You will never choose 0 units of x. Is that clear? Yes. Okay.
Sir, could you repeat this once?
Yeah. Just take, what is the interpretation of the derivative? How do you interpret the derivative? Derivative tells you whether if the sign of the derivative tells you whether the function is increasing or decreasing, right? So what is the sign of the derivative when x is close to 0? Negative, right? What is the sign of the derivative of the objective when x is close to 0? It's negative, right? Because this term dominates, right? And when x is close to 0, this will be close to infinity, right? So the
Yes.
sign of the derivative of this expression is going to be negative when x is close to 0, which means that this particular expression, which is your cost or whatever expenditure, is falling in x. As you increase x, your expenditure is reducing. So it makes sense not to choose x equal to 0, that's for sure. Is that okay? Now
Right,
notice
sir. Got it.
that as x increases, what happens to the value of the derivative? Initially it is negative, it becomes flatter and flatter. At some stage it reaches the bottom, and then it starts going up like this. Why can I say that it starts going up like this? Because as x approaches infinity, the derivative approaches px, which is positive. So initially you can see that the sign of the derivative, right? I mean, it is negative, then it becomes like less steeper, it becomes flatter, and then eventually it becomes flat like this, where this term will be 0. That's where the derivative is 0. This is the point where derivative is 0. Is that okay? So if I plot the graph of this expression, this is how it's going to look. Now, what is this point? How will you find out this point? Where is this bottom? Bottom, where is this bottom of this graph? It is where this derivative is 0, right? Because that's where the derivative is 0, right? Can you tell me what is this value? What is the value of x at this point? Do you agree?
Yes, sir.
Now notice that x can only take value between 0 and mu square by 4. Okay. So if mu square by 4 is to the left of this point, if mu square by 4 is here, then can you tell me what is the optimal choice? Because
Mu
I
square
mean,
by
it
4.
depends on where mu square by 4, right? And if mu square by 4 is here, then what is the optimal choice?
Py by px whole square.
Then what is that's right. Okay. So there are two situations. One is py by px square is less than mu square by 4. Okay, in which case x is py by px square, and if py by px square is greater than or equal to mu square by 4, the optimal choice will be mu square by 4. And notice that this is exactly the same thing that we wrote earlier. If you remember, the conditions that we wrote were, you can just write this as mu by 2, write this as py by px. So you can just write this as px by py is greater than 2 by mu. Okay, and this condition can be written as px by py is less than or equal to 2 by mu. Right? So this is the same thing as this, right? And this is the same thing as this. And you can just check your, what we did earlier, and check that this is exactly the Hickson demand that we got. Okay, so this is an alternative way of doing the same problem. Okay, basically you are checking, as you are moving along the indifference curve, how your expenditure is changing, and you would like to reach the point where the expenditure is the least possible expenditure on this indifference curve. Okay, so it depends on the positions, of py by px square relative to mu square by 4. If this point happens to be to the right of this point, then this is the optimal choice because that's where the bottom of the graph is. And if this point lies to the left of this point, in which case, you are choosing, so basically if this is the case, then you are choosing the best point in this region. Basically from this point to this point, you are choosing what is the best point in this interval, and in which case, it will be mu square by 4. Fine. And now that you know what is x, you can figure out what is y. How do you figure out what is y? Y is nothing but mu minus 2 root x. So you already know what is x. So yh is mu minus 2 root xh. So that's how you can calculate the value of corresponding value y, that you will choose along with this x. Is that fine?
Yes, sir.
Okay then. Okay. Okay. So please, try to use multiple methods to solve a single problem. That will, actually help you in many ways, because the more methods the faster you will be in choosing the right method when you are doing the exam.